Okay, so what I want to do is I want to give you a little introduction to three-dimensional vectors. Now, I know you've seen this in your Calc 3, but this will just be a little extra help in case sometimes it's helpful to see things from a different perspective. All right, so here we've got a nice XY coordinate system, and I'm going to stick a vector on here, and let's put it in the first quadrant, and let's call it vector R. Just like that. And we have talked about how we try to label vectors and how we work with vectors. And we know that we could write here R is Rx I hat plus Ry j hat. And if we knew this angle right here, let's say that's theta. Actually, you know what? I don't want to call it theta. I want to call it alpha. Okay. So if we know that that's alpha, then we can write this as R cosine alpha I hat plus R sine alpha j hat. Okay. Nothing new there, only writing stuff down that we've already known about. Okay. Um, but let me kind of shift this just a little bit to this other notation with the brackets, and we can say it's R, which is the length, the magnitude, onto cosine alpha, comma, sine alpha. Okay. Now, when we do that, we know also that in this case, well, in all cases, I guess, cosine squared alpha plus sine squared alpha is equal to 1. Okay. But let's suppose, just for grins and giggles, that we come up over here and we call this other this angle here beta. Okay. And they're complementary. So if alpha is 30, beta is 60. Okay. So that's how we're setting this up. If we did that, then we could say that our R vector was actually R magnitude onto cosine alpha, cosine beta. All right. Now, there's different ways to think that through. One way to think that through is that cosine always has to do with the adjacent side. And so that's going to be, if we go with cosine, that's going to be this right here. And for my alpha, it's going to be that right there. So I've got my Rx and I've got my Ry with those two lengths right there. Okay. So that's one way to think about it. The other way to think about it is just to realize, which I'm sure some of you are way ahead of me on this, cosine beta and sine alpha are the same thing. All right. Those guys are the same thing. All right. But what I want you to see is if we use this notation, we get something that's just a little bit kind of like, it makes sense, but at the same time, it's kind of like, oh, I never thought about it that way before, which is to say that cosine squared alpha plus cosine squared beta is equal to 1. Okay. Hopefully my internet will catch up. There we go. Cosine squared alpha plus cosine squared beta is equal to 1. Okay. So move my picture out of the way. I feel like I'm in the way there. Now let's go to make my screen bigger and kind of let's duplicate this in 3 dimensions. All right. So now I've got my 3-dimensional coordinate system. So I got my, instead of quadrants, we've got octants there. And let's put the same vector out there. So we got a vector out here like this. Okay, so there's R. And R's in the XY plane. And we've got the same components. So there's our angle beta. And here's our angle alpha. Just like this. Okay. Now, let's suppose for just a second that we didn't know that this vector lay only, that the vector lay in the xy plane. Let's suppose that we only know alpha. So maybe alpha is 30 degrees, okay? That's all we know about this thing. Alpha is 30 degrees, okay? What would that tell us? Well, what it would actually tell us is that there's a cone around the x-axis here, okay? Not a very good cone. I don't know. Hopefully you can tell that's supposed to be a cone. Okay. But my vector is out there. Here's my x-axis. Any angle around that, like a cone, the angle of the cone is 30 degrees. Okay. And my vector could be anywhere on that cone. After all, anywhere it is on the cone, the angle is still 30 degrees. Okay. Um, so let me get rid of my beautiful cone there. And let's think about our other angle here. Over here, this guy beta. What if all we knew was that our vector r was 60 degrees off of y? What if that's all we knew? Same sort of thing. We would have to have some kind of a cone like this. All right. And we know that our vector would be 60 degrees off of the y-axis, but we don't exactly know where it would be. Okay. So what I'm trying to get to you to think about is that if we only know it's 30 degrees off of x or it's 60 degrees off of y, that's not really enough information. Okay. We need these two angles. Okay. So let me get rid of that guy there. Boom, 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 boom. Oops. I wanted that back in there. Okay, so we've got that to be true too. Now, if we know both of those things, and I'm not going to try and draw this because that would be too crazy. If we know both those pieces of information, alpha, that gives us a cone this way, and beta gives us a cone over here, those two cones are going to touch each other. And and exactly the one line where they touch each other is our vector r. Okay, so you might grab a couple of solo cups or something and be like, oh yeah, okay, all right. So that's how that works. Okay, but let me change this up. Let me get rid of all of this and let's make it a little more interesting. Let's suppose that instead of alpha equal 30 degrees, I better write this down. So suppose that alpha is 40 degrees and beta is, I don't know, instead of 60 degrees, not 50 degrees, but well, maybe it still is 60 degrees. Let's leave it at 60 degrees. Okay. Now alpha and beta aren't complementary anymore. They're not complementary anymore. Okay. So what does that mean? Well, if we're using it to define a vector, it still means that the vector is on a cone that is 40 degrees out from x, somewhere. We don't know where, but somewhere. And in terms of the y-axis, it's still 60 degrees out. Okay. But now, if we think about where are these two cones going to touch each other, they don't touch in a line, they touch along two lines. So they're kind of like laced together. I don't know if that makes any sense. So if you could have one solo cup and pass the other solo cup sort of through the wall, you'd get an intersection there and you'd have two lines coming straight out. So our intersection of the two cones, one would come up here and the other would come down here. Both of these are going to lie on the intersection of the two cones. Okay. Now, if it's a vector, then we're going to have more to go off of than just alpha equals 40 and beta equals 60, because if we do that, then we've got two vectors and we don't know which one is which. Okay. So there's ways around that. One way around it is we just flat out say the z component has to be positive. If the z component is positive, then we get the guy on top. Okay, boop, we're done. On the other hand, we could say z is negative. If z is negative, then we get the one below the xy plane. All right. So we would have to know the angle around the x-axis, the angle around the y-axis, and if it's above or below the plane. Okay. So if we know those three pieces of information, we can define our three-dimensional vector. Okay. But wait, there's more. Let's suppose we provide one more piece of information, and that is the angle here, let's call it gamma, from the from the z. Okay. Now, in our case of the two vectors, gamma could look like that, or gamma could come all the way down here like this. So we've got two options for gamma. We don't really know which one it's going to be. So we would still have to be told if it's above the plane or if it's below the plane. Okay. But how can we get the actual number for that, for the value of gamma? Can we get that number? And the answer is yes. And the answer comes from the fact that we can write that cosine squared alpha plus cosine squared beta. Okay, in 2 dimensions, that's equal to 1. We saw that already. But in 3 dimensions, if we add cosine squared gamma, then we're in business. Oh, I gotta move my picture again. I'm in the way of myself. I'm in the way of myself. There's a good Zen meditation saying there, right there. Something to dwell on, but another time. Okay, so cosine squared alpha, cosine squared beta, cosine squared gamma. So we could figure out what we needed for gamma to be. Okay, and so if we wanted to do that, if we do a little bit of algebra here, we're going to have cosine squared gamma has to be 1 minus cosine squared alpha minus cosine squared beta. So I'd have 1 minus cosine squared. See, we said 40 degrees. We're just making up numbers. Cosine squared. 60 degrees. We're just making up numbers. And so that's going to get us some answer. Okay. Let me, I'm going to pause this recording and go get that answer. Be right back. All right. So what we get is we get that gamma turns out to be 66.2. Now, when you do that, you end up with the square root situation. So we're going to have to say here, really, when we take our square root, we're going to have cosine squared theta is some number, which I don't remember what it was, but cosine of gamma is going to be plus or minus the square root of whatever that number happens to be, okay? And so the plus solution gives us gamma measured from the top, and the minus is going to give us the angle measured from the bottom. Okay, just like that. All right, but the take-home point here that I want you to know is that we have another way to specify a three-dimensional vector, which is, what did I say that was? 66.2 degrees. All right, so I can use these angles, and these are called direction cosines. So if I have a magnitude and I have a direction cosine, then I can get all kinds of information about my angle. Okay, so it's under the right circumstances, it's pretty handy. Okay, it's maybe not super generic. All right, so you can't always use this for different things, but it's often useful. And when we do some examples in a little bit, some later videos, I'll show you how it can be used. Okay. Now, I want to show you one other thing about three-dimensional vectors. Okay, and I know you've probably seen this in Calc 3, but again, it's kind of good to go over it from a slightly different perspective. Let's suppose our vector r is up here. Okay, and we know that there's an angle in here. We called that gamma earlier. But now we're not going to use direction cosine notation. So we're going to use a different notation. So I'm going to give you a different notation. But we called it gamma. Now we're going to call it theta. But you need to know it's the same thing. Okay. Now what that thing does is theta, if we shine a light up here, then there would be a shadow right down here in the XY plane. And that shadow would be, technically it's called the projection of R onto the XY plane. Okay. But that shadow is sort of directly below our vector there. And then the angle from the X axis over here, we're going to call that phi. Okay, those, it's pretty traditional demarcation to call it, or notation to call the angle off of Z, theta, and the angle around X to call that phi. Okay. Um, Now let's call the vector that's in the XY plane, I like to call it the shadow vector. I don't know if that's correct, or if there is a mathematician here, they would scold me, but you get the right idea here. Okay. It's the shadow of that thing. So what we got is we've got r theta phi. So it's a magnitude, an angle, and then two different angles. Okay. And so if we've got the magnitude and these two different angles, we can work out the different components because, well, RZ is the easiest one. RZ is just going to be the magnitude and cosine of theta. All right, that's all we need there. Okay. Now to get the x component, our x is, okay, so follow carefully here. I'm going to say the shadow vector, r sub s, times the cosine of phi. The shadow vector times the cosine of phi. All right. Now the shadow vector is actually r sine theta. So what we get is r sine theta cosine phi, just like that. All right. So kind of learn to break it down in your head. Magnitude, the part that's in the xy plane, scooted it over the part that's along x. That's all we're doing there. Okay. The part that's in the xy plane, the part that's along x. That's all there is to it. Getting r sub y is the same thing. So r sub y is that shadow vector. And except this time it's going to go as sine of phi instead of as cosine of phi. So sine is the way the angle is given to us there. Sine is the opposite side. And so we can work it out that way. Writing in what the shadow vector is, we're going to have r sine theta sine phi. Okay. There you go. Pretty straightforward. Now, let me tell you about a couple of things to watch out for. So, first of all, you might end up seeing something like this. Okay, so what do we do if we have something like that? Well, don't panic. It's not a big deal. Okay, they're giving us a lot of information when they give us that little bitty triangle there. What do we need? We don't actually have to know the angle theta. Remember, what matters is the cosine values and the sine values. So if I had something like that, all I would do wherever, oops, what did I? All I would do wherever I have a theta is my cosine. Okay, if I look at my triangle, cosine is the adjacent side. Okay, so it's the length of interest. So it's going to be 4/5 as I've drawn it here. And then all my sines are going to turn into 3/5. Okay, so they've kind of done, once you understand it, they've kind of done the work for us. Okay, so you might see that. We might also see something similar to that down here. Okay, let me call that 3 and a 5. Oops, not a 5, a 4. Okay, so maybe we've got a 3, 4. It gives us a 3, 4, 5 triangle in the XY plane. Okay, so if that happens, okay, it's the same sort of thing. We just look at cosine. All right, cosine has to do with the adjacent angle. Now, in our case, what we need to do is realize that we need the x component of our shadow vector, and the side that's got the 3 is parallel to that. So cosine phi becomes 3/5, and so sine phi becomes 4/5. Okay. So now let me warn you about something. All right. Many of you, and this is perfectly natural, many of you are going to immediately jump to thinking, if I need X, I use cosine. If I need Y, I use sine. As strongly as I can tell you, you need to move away from that. That's a trap. Okay. That's a trap. You need to adjust your thinking. Instead of X cosine and Y sine, you need to start thinking, what's my adjacent side? What's my opposite side? That's what you want to go for. So if it's an adjacent side, go cosine. If it's opposite side, go sine. All right, because you don't know what they could do. They might do something really screwy and give you this angle instead of theta. Okay, or something else. All right. So make that adjustment to using sine and cosine, and then you'll be in good shape. Okay. All right. In the next few videos, I'll show you how we're going to use all this stuff in different situations.